come back and you'll have time to look at them and discuss the grading. I would say maybe Friday, but I don't want to promise. Maybe next Tuesday. So we are doing graphs, and we'll start with a quick recap of what happened last time. That camera doesn't seem straight. Can anybody look at the camera screen? You can see the whole board? So, last time we said BFS and DFS traversals each traversal produces a tree, also called advancing tree. This advancing tree, either BFS or DFS, contains edges as a subset of E. So, in other words, if I have a graph and I look at the may have another run here. So what I just draw here is the advancing tree. So I have a BFS or DFS that starts here, and maybe another run that starts here, right? So this is DFS run 1, and this is DFS run 2. We said this last time. I may need more than one run to traverse the whole graph. This is the advancing tree, the one that discovers new nodes. I might have other edges here, right? I might have this edge. That's possible, but it's not used by DFS. I may have this edge. That's possible, but not used by DFS. Is that possible, this edge? Can I have this edge here? And DFS not use it? How can this happen? If I look at this edge here, and I say, it's possible to have it, but DFS didn't use it. Why didn't use it? Let's call this A, B, C, D, E, F, G, H, I, J, K. So how come, if you went BF from S, wouldn't have used this edge?
Yes.
But how is it possible not to use this edge? It went C first, then D. Now, since D is done here, by the time I get to F, I don't need to use this advanced edge, right? So how about an edge from here to here? Is this possible? Can I have an edge here, like that somehow DFS does not use?
No.
How?
If we start from I.
If I start from I, although I say run 1 here, I think run 1 means it's the first run, right? If this is the first run, this is not possible because DFS would have used this edge. But if it starts from I, like he's saying, if I start from I and I get to these two, then when I'm at A, I don't need to use this edge, right? Can I have an edge from here to here? Is that possible in my graph and DFS not using it? Same thing. If I start from A, this is not possible. After G, I would have gotten here, and I wouldn't need a run 2, because once I get here, I traverse these edges. But if I start from I get to here, I'm done, and then I have to start another run from A. By the time I get to G, this will be gray 2, black. Right? So the edges that DFS uses form a tree. This is a subset of the original edges. And there could be some other edges that are not used in here. So let's say DFS edges. I want to say before that this BFS has a wave time. Right? BFS, every node gets labeled with the wave that it's at. And DFS has what? Has a discovery time and finish time. Okay? For each node. So now in edges, we have the advance for 3 edges. How those go? What's an advance edge? I'm in a gray node, one that I'm exploring from but not finished, towards a white node. So gray is started and white is not started. Right? I can have what kind of edge? A gray to gray, what is that? This is a back edge. So what's if I have this, who started first? Who's discovered first? Is this one discovered first? Can I be this one? Why? If I discovered this first, this would be white when I discovered this one, right? And then when I see this edge, that's white. Not necessarily. Right? So I discovered this node first, like I'm saying. I think you guys are right. If this is the case, then this one must be discovered first. Let's write that down. D, discovered first. Why is that? Suppose this one is discovered first. If I see this edge when this is white, then this is not the situation. It's not gray to gray, it would be gray to white. How is this possible? Maybe I went through some other edge first. So this is discovered first. I get to some other edge here. And from here, I get to here. Right? And then I discovered this through this route. Why is this not possible? Why, when I look at this edge, this is not gray to gray? If that would be the case, if this is discovered after through a different route, which is possible, what would be the situation when I look at this edge? It will be black, because once this is discovered after, there was a theorem that says this must be finished before this. Right? So this is got to be discovered first. Back edge means a cycle. Right? So it's a standard way to decide to find cycles. I have a back edge. What else can I have? A forward edge. Was it what? Gray to black, but which one was discovered first? I forgot in the forward edge. Gray is first? And cross, I think it's called, edge, is the same situation. Only this is discovered first. And we have a theorem about discovery and finishing times. If something is discovered and then another node is discovered, there is a situation that's not possible. So there was a theorem that says the following is not possible. You can discover something, some node, then discover some other node, then finish the first node, then finish the second node. Because this is not possible. It's either discover node, finish it before discovering the second one, or you discover V, then finish V, then finish U. Right? This is not possible. Okay. So that's about DFS. DFS is quite the basis for a lot of things with graphs. So I think BFS it's easier and people have a very nice intuition about it. But DFS, it takes some time to settle down. Even though I know you studied as an undergraduate, DFS is more complex than it looks. So then, I talked about strongly connected component, no, topological sort. You guys, that was supposed to be an exercise. Did you figure that out? Topological sort. So if a graph is a DAG, that is direct symmetric graph, no cycles. I'm going to add something simple. Typically means, or standard, means no edges to itself. So an edge to itself looks like this. This is some node M and an edge like this. When somebody says simple graph, it means there's no these funny edges from a node to itself. But in general, I could have such edges. This is not forbidden by any norm. So about the Graphs Scc graph, what happens is there is a, it could look like that. There's no cycles here. So the theorem says there is an order to sort all vertices on a line such that all edges go left. Did you solve this exercise? How do you do this? How do I sort all the nodes? I want to put them on one line such that all the edges go one way. This is a simple problem. I want to sort these edges, these vertices, and arrange them, all of them on one line, right? So let's say A, B, C, D, E, F, G, H. That's a good order, right? A, B, C, D, E, F, G, H, I think. If I use them in this order, I have edges from A to B, and I have edges from A to C. From B I have to E and G. From C I have to E and F. From D I have to E. From E I have to F. From F I have to G. And from G I have to H. I could have another one from D to H, for example. Right? See how I can put them on a line so that all the edges go from left to right. How do I do this?
We can order by sync node. We can take the nodes which have no outgoing edges and then add on the left hand side.
So you're saying take the nodes that have no outgoing edges like A.
No, like H.
No outgoing edges, okay, H. That goes on the right side, right? And then what?
And then remove it and remove all the, for example, T has 1, 2, H, so we remove that arrow and then add T the left hand side.
Okay, so I think that works. Either from the left or from the right. He's saying, take all the nodes that have no outgoing edges. And I think he implies the order among those doesn't really matter. So suppose I have another node like H, I'm gonna add one, node I here. And I'm gonna say there is two edges from, E and from B. So that node I, by this mechanism, could go anywhere in here. I'm gonna put I in here, and I have to draw the edges from B to E, B, and from E. I could have permuted H and I. These nodes that have no outgoing edges, they form a set of nodes that it doesn't matter how I sort them in between. Because in between them, there is no edge. Why is that? If I look at only the set of nodes with no outgoing edges, why can't I have an edge between H and I? There'll be an outgoing from H or from I, right? So because there's no edge between them, doesn't matter how I sort them. I could have sorted IH instead of HI, would still be a valid topological sort. So now that I have H and I, what should be the next group of nodes to my left, immediate left? All the nodes pointing to H and I, but those have to be sorted somehow or not? How?
Which are connected.
I have to use the same principle if they have no outgoing edges other than H and I. So no, edges going to H and I are now settled because H and I is at the right side. So I don't have to worry about nodes going to H and I. Those will be going the right order. But I want to worry about a set of nodes. Again, edges to H and I settled because I put them here. But I want out of these nodes to select the ones that have no other outgoing edges. So I apply the same principle. I say I want nodes that have no outgoing edges except H and I, because H and I, that's fine, they're already at the right side. So which should be the nodes that have no outgoing edges other than H and I? G qualifies? Why? There's only one outgoing edge, that's H and I. So that'll be G. Who else has no other outgoing edges other than H and I? Is E qualify? No. Actually, F doesn't qualify because F goes to G. Who else qualifies? Nobody else, right? So my next group is G. This is okay to put in here because all outgoing edges from G have to go to H and I. Therefore, I know this will be on the right side. I keep going this reasoning. What is my next group? All that have no outgoing edges other than G, H, and I. Because if they have those outgoing edges, they're going to go to the right side. So which are my nodes that have no outgoing edges other than, so G, H, and I are allowed, but nobody else. B qualifies? No. E qualifies? Yes. F qualifies? E qualifies? No. F qualifies. How about D? So that's F here. Again, all the edges that are going are to G, H, and I, which are to the right side, and there's no other outgoing edges. Can we see that doing this reasoning, we get to sort it correctly? Hands up, who's with me? Good. How long will it take to run this algorithm? Find the nodes that have no outgoing edges other than the ones I already put on the right side. So initially I have H and I have to find all the nodes now that have no outgoing edges to H and I. I found G, I put G there, and I'll find all the nodes that have no outgoing edges to G, H, and I. How long would that take? N is what? So in graphs, we have two parameters, and we want to keep them separate, v and e. And if we say n, we mean the size of v. But most graph algorithms are written in terms of v and e. So we don't say n, we say v and e. So e is the number of edges, v is the number of vertices. In a connected graph, e must be at least v minus 1. And the maximum size of e is v squared. So this algorithm that I just said here, once I have a bunch of nodes, how do I find the other nodes that have no edges other than, say I got G, H, and H. How do I find, okay, I need F now?
Adjacency list.
Hmm?
The adjacency list.
So I delete these edges? Know what you're saying?
Using the adjacency list, we can.
Right, but how long it's gonna take? Once I decided to put G, H, and A, I have this part done. This part right here, that's done. I need to find the next group of nodes, which happens to be just F, right? How much running time I need here to find this F? How would I do it? You're saying go to the incident list and mark every node that has an outgoing edge to G, H, to anybody else than G, H, and I. I think that's an expensive algorithm. Because I have to do this for every group, right? Once I put F, then I have to repeat this process. If I go to every single vertex and I check the outgoing edges, overall, my running time for that step is E, right? Because I'm going through every edge once. So that's of all V, but I have to do it for every group. That seems expensive. How about every time I put those nodes down, I remove the incoming edges, right? So I put this node, I remove the incoming edges, and I still ask for nodes with no incoming edges, right? So what happens here, if I put those nodes down, as soon as I put G, what was the first one, H and I, remove incoming edges. Then I put G, remove incoming edges to G. I need to keep track for each vertex of the number of incoming edges, right? Every time, initially the number of, outgoing edges for F was what? 1. For E is 2. Every time I put this node down, I have to remove the edges incoming to it. And then once I do G, I, and H, what will be the outgoing degree of E after removing the edges? 1, only to F. How about the outgoing of F? 0. So at every step, which is the next group of nodes? The ones that have 0 outgoing degree. Degree is the number of edges incident to a node in an undirected graph. If it's directed, you have to keep track of 2 degrees. Incoming degree, how many edges are incoming to the node, and outgoing degree, how many edges are outgoing from the node. So in this situation, after I have G, H, and H put down here, after removing outgoing edges to those nodes, the only node that has degree 0, outgoing degree 0 is F. So F is my next node. So if I do this, overall, how many edges I have to remove? Not just in one step. The finishing total procedure. Every edge is removed once, so I have to remove total E edges. That's okay. And then, once I have the removal done, that's OV total, how do I have to keep track of the nodes that have 0 outgoing degrees, right? Because I don't want to, at this step, I don't want to say for I equal 1 to V, check if we have 0 outgoing degree, and if it does, put it there. I need some sort of data structure to help me out to say, okay, because if I do that, I run this procedure, just check for all nodes all the time. I don't run it all the time. So assuming I'm dealing with the removal of edges, OV total, because every edge is only removed once. How do I know at this point, after I've done with G, H, and I, how do I find this F quickly? That's the degree 0, outgoing degree 0. Keep track of some sort of heap or some data structure that allows me to say everybody has the minimum outgoing degree. Maybe multiple nodes that have 0. Just I'll extract them quickly. So overall, that should be if I do that, of what? Of 1 for 1 extract mean, but then I have to go for everything. That's probably like V, right? Okay. So the efficient algorithm would use V steps for the nodes and E steps to remove the edges. We write that down something like V plus E. V plus E in asymptotic notation is linear in both V and E. We call this linear for graphs. And it's either V or E, whichever one is bigger. Typically, E is bigger. Only very sparse graphs have V bigger because the graphs with V bigger have to be disconnected. Right? Most graphs, even if they're disconnected, E is roughly at least V. Otherwise, it's a very sparse thing. Right? How about, I'm going to stop for a second. How about DFS? What's the runtime of DFS? This, I'm skipping this for now. I'm not looking at it. I'm just, okay? I don't want you guys to look at it. If I do this, how do I implement DFS? I'm in a node, and I'm in that node. I check all the outgoing edges, and I say what happens. If it's a white node, advance. If it's not a white node, classify the edge, da da da. I already advanced to the white edges. So how many? What's the running time? V times E? Are you sure? How many times I process or consider an edge? Once. So I'm only, all the edges that are in the graphs, including the non-advanced edges, are only considered once. Once I consider an edge, I decide immediately if it's an advancing edge, if it's gray to white, or if it's a cross edge or back edge or whatever. But I'm never considering that edge again. So this is going to be E, the number of edges. And now, what happens to the vertices? I think it's typically O of E, because it only considers each edge once, except if this graph is very disconnected, it has to do a lot of runs. So that's going to be plus V. You should know how to prove this, by the way. You should, if you get a question, prove that the runtime of DFS is asymptotic E plus V. That means whichever is bigger between them, right? You should know how to prove this. So really considering the pseudocode of DFS, why the runtime is E plus V. That's a required part of the matter. It's very easy, because you look at the DFS steps and say, I'm traversing each edge once, and then what am I doing in a node? I'm not doing much work in a node other than considering the outgoing edges, right? And set up the discovery time, set up the finish time, all of that is all of one operation. The edges, if there are many edges, I have to go through all of them, but that's the O of E plus, O of E time. And I'm going to say BFS also, V plus T. You can check that at home. That's even easier. Now I want to go back to this problem. Say, instead of doing all these removals, can I be smart and use DFS instead? Because I notice the runtimes are the same, V plus C, V plus C. Can I run a DFS and then sort somehow? The procedures we just discussed, I think it's correct. Removing the outgoing edges and then putting the next group of nodes that have the outgoing degree 0 and repeating that, it's going to create a correct topological sort. But topological sort, that only applies to DAGs via DFS. So I'm going to run DFS, of course, and then sort vertices by what? Finish time. So where should be the big finish times? I mean, in what direction do I sort them? The big finish times should be, if I run DFS in this graph, what's the big finish time? Who finishes last? A. So this is big finish time. So big F towards small. Sort them in this order. Why this works? What are the edges in here? So how do I prove that this is a correct sorting? What I'm essentially saying here, if you sort by the finish time, all the edges gonna go to the right, left to right. So why is that? If I have an advance for 3 edge, that's from gray to white, right? Gray to white. Which node is going to finish first? Right. So this is the small f. Let's just say the f of this gray, the finishing time has to be bigger than. Right? This is because of DFS nature. If this is discovered from here, we call this an ancestor, right? Then this has to finish before I finish the ancestor. So would that work in my sorting here? Which one will get a smaller finishing time? The white one, which will be sorted on the right side, and the edge will be left to right, right? Because it's from big F's to small f's. How about what other edge I have there? Cross edge. This goes from gray to black. And what was in cross edges? Which one is discovered first?
Black.
The black. This is discovered first. Discover of black is smaller than discover of gray. Right? And how about the finishing time? Who's going to finish first here? Black is already finished when I look at this edge. That's why it's black. Black means finished, right? So the finishing of black has to be even without the discovery inequality here. Just because this one's black, this one's gray, means this one's finished already and this one's not finished already. So this finishing time will be larger. So is that okay for my sorting? Is the edge going to go left to right? This F is going to be bigger, therefore on the left side. And the last one that we need to consider? Forward. It's still gray to black, right? And even without looking at discovery, just because this one's black, it means it's finished already. Right? Same thing. Finish of black, it's already done, and this one will finish later. So it'll have a higher finishing time, which means my edge is going to be from left to right. What's the only edge that would cause me a trouble? Back edge. A back edge will have the finishing time on the gray, right? It'll be gray to gray, and the finishing time will be backwards. A back edge will have to go back. But I don't have back edges because this is applicable only to no cycles. A back edge indicates a cycle, but I don't have back edges here. So topological sort of V plus E, reverse order of finishing times, and every time you see a DAG, the first thing you should think of is topological sort. In fact, you should think of DAGs as sorted on a line. That's how you should. When you have a DAG, don't draw it like this. Think about it on a line. And then a lot of algorithms will work much better because they will have to go through edges in certain order. Yes?
For the level sort, the runtime, how can you know which edge to remove? Because you said each edge will be removed once.
Right. When,
But
not this procedure, the first one we discussed, you mean?
No, I mean, how could you know which one to remove? Because you said the runtime is only V plus C.
Right, so I think you're asking when I decide, this is the first procedure we discussed, not the second one. When I put G, I say remove all edges.
That's, you have to traverse all the edges.
Are we going to G, right? And I think he means to say, if I keep those adiacents list I talked to you last time about, how can I remove just these outgoing edges? Because those adiacents list contains the outgoing, not the incoming edges, right? So it'd be very convenient to store, to say for G, store not the outgoing from G, but the incoming to G. That way I could remove him right away, right? I put this G, boom, remove the incoming. So I think it's a very good point. If I use those adiacents lists, remember? There was a vertex U and then it was going into, let's take an example here, say E, right? If this is E, the edges were going to I and then a pointer to what? F. And then another pointer to? No? Is that right? That's what this stuff was stored. For each node, store the edges in a linked list. His point is this data structure is not very useful because once you have decided on G, you would like immediate access not to the outgoing of G, which are printed there in that list. You want the immediate access to the incoming edges of G. So what do I do? I need to, before start this, go through that data structure and make a dual data structure that stores the incoming edges. Right? If I would store this not as outgoing edges but incoming edges, I can do my algorithm here. And I think I can replicate this structure just by traversing all edges once. I could go through all this list once, all the edges here, all of them, and replicate the data structure into outgoing edges instead of incoming edges. So I need this pre-processing step that takes my adiacents list and make it the incoming edges rather than outgoing edges. Good point. So I will need that before I can run this operation. Of course, in practice, we just run DFS and do this. This is the typical standard method for the topological sort. Again, many algorithms will run much faster on DAGs after a topological sort than on general graphs, because I can process, once I have the topological sort, I can process the vertices or the edges in a certain order. Algorithms will get simplified. Things like shortest path, we'll get to there next time. It'll be much faster here than in a general graph. Okay? We're good? So what, yes?
But even if we are storing the incoming edges, then still we need to traverse it again, right, from the beginning to end to see that which one is not having anything now. How can we directly pick up a node?
Remember when we remove an incoming edge to G, we have to update the degree of this guy. So we have the outgoing degree from 1 becomes 0. And I need now the other data structure to figure out how to extract min quickly. So there's the other stuff that has been discussed. If I remove this edge, which I can do it by OV total. His point is, every time I remove this edge, now my data structure will, what will be the linked list in G if I keep track of our incoming edges, not outgoing. From G, which ones will be linked to G? F and E. So when I go through that, say remove the edges, the incoming edges, I decrease the outgoing degree of E by 1 and the one of F by 1. But now I need a quick way to say everybody who has outgoing degree 0 is my next group. Now, of course, if I decide that's F, it's easy to go in that linked list of F and say remove more outgoing edges, right? The question is, how do I decide F pretty quick? Right? I don't want to do too much effort. I mean, the degrees are updated, but I need to find the ones that has degree 0. What people do sometimes, how could I do this if I don't want to complicate myself with groups? Here's how I can do it. When I remove edges, I keep a list, or an array, a very temporary or auxiliary array that creates this group. I want to keep a list of all the nodes which have degree 0. The reason I can keep this list is that when I'm putting the next group, it will be, I'm flushing that list out. Everybody who has degree 0, it's in that auxiliary list. I'm writing them down, now my list is empty. So then, what happens when I remove an edge? I keep track of the outgoing degree, and if I notice the outgoing degree becoming 0, I do what? Put that F in that list right away. That will be a list that gets flashed with every group, right? At the end, after updating my degrees, I look at that list, everybody in the list, boom, is my next group. The list is empty now. I go through those ones, I remove, so I'm putting F, right? Then I'm gonna put E. Then I'm gonna remove these edges coming to E. I'm gonna update the degrees of these guys. And the list is empty now. Everybody who gets degree 0, keep track of it, put it in the list. So I don't have to use a heap with extract min and something like that. I just have this temporary list that just keeps track of the nodes that I notice have degree 0, so I can put that list down. Maybe I should write pseudocode, because I keep talking, and I don't know if you guys follow me, okay? So it'd be useful to make some note there, okay, how can I write down the next group that have degree 0? Maybe every group, when I start processing the next group, updating, I flash that list, printing down, and then for every node that has degree 0, putting in the list for the next group to be printed down.
So when we store these nodes, won't we even have to put some effort to search for it? Because it would be maybe part of some array or tree or heap itself, so we have to search for this element?
I think that's exactly the question being asked. How do I know which nodes become of degree 0? Initially, I have to find the nodes of degree 0 the first time. But then, every time a node gets to have degree 0 by an update, I have to keep track of it immediately. So I don't have to search for it.
Before you update, you have to look for F in all the node set.
That's what we said in here. We would like to reverse that adjacent list. Instead of keep track of outgoing edges, which is the standard adjacent list, keep track of incoming edges. So instead of having something like this, we would have what? The E will be pointed to what? B, C, and
D.
D. Right?
Yeah, so
If I keep track of incoming edges, every time I put E down, I can remove those edges.
yeah, so now I'm saying that you know you have to go to B. Is there no effort to search for B in your?
No, because I just go through this list. I go through this list, I remove those
so these
edges,
are the points.
and I decrease the
Okay.
incoming degrees of B, C, and D, and if they become 0, put them in my list for next round. I mean, you still have to work out these details. That's not how it's being done. This is how it's being done. So I don't spend a lot of time with something that's not. I think you can still run it in all V plus E, so that's valid. But what people do, the BFS is so well implemented these days. If you want to run DFS, just run DFS and use the output of it. And the truth is, you can sort by finishing time and be done. I need to move on here. What else did we do that we actually didn't quite finish is strongly connected components, right? So let me go to that carefully. I'm going to have a graph here. So SCC. Here's a graph. First of all, what is strongly connected components? Are subgroups of vertices where all u to v are reachable. In other words, there is a path in that subgroup from any node to any node. So what are the subgroups in here that are reachable both ways? ABE, that's a subgroup. What other subgroup is and this one, right? So I would like to write this SCC before I show you an algorithm how to find those connected components. As more like, I'm going to group them. ABE is one SCC. Then I have FGH is another FCC. Then I have CD is another SCC. And then I have I. So I'm kind of grouping them as one group for the purpose. This is not, this is analysis of what's going on. Of course, like in dynamic programming, when we talk about the optimal solution, I don't have those groups. I have to find them. But I'm saying if somebody would find them for me, what would be the property that they have? This is for me to think about what kind of algorithm to run to detect them. So the problem here is detect the strongly connected components. What's now the relationship between these groups? If I were to, in terms of reachability, from AB, where can I reach? I can reach here. I would like to add an edge that I miss here. Doesn't change the strongly connected components, just to make it more interesting. So from AB, I can reach here, right? And now from here, I can reach to I. And from this group, I can reach to I. Is that right? I can also reach this way? So my first claim, theorem, SCC form a DAG. Say DAG capitals. In this graph, once I group the SCC together and I put the reachability edges, I don't write multiple edges, even if from this group to this group, how many edges are in the original graph? Three. This edge, and that edge. In terms of reachability, I only put one edge, right? From this group, AB, I can reach to FGH. So this edge here, it's all edges that are what? EF. What else? BF and BG. Right? Those three edges are all reaching from AB to FGH, so I'm only putting it as one edge. Okay? Do we all agree this is a DAG? Why can't I have a cycle here? If there will be a cycle, meaning from CD I go back to ABE, and this will be one connected component, because if I can reach this way, in here I can go from everywhere to everywhere and go back. It means I can reach from everywhere here to here and from everywhere here to here. That would be an SCC. SCC are maximal. So we don't take just A and B if we could take A, B, and E. We take the maximum subgroup that's reachable of everybody to everybody. So I think everybody can agree this is a DAG. Now, how can I detect these components? So again, I don't have them, but I'm doing an analysis here if I have them. In a DAG, I remember from the DAG problem, there is some nodes that have no incoming edges and some nodes that have no outgoing edges. So since here so happens is that if I do a topological sort, for example, I would get ABE is the group with no incoming. And what's the groups that have no outgoing in my example here? I. This group has no outgoing. Here's my point. In a DAG, how can I detect a component like I if I start the traversal algorithm in I, either BFS or DFS? That traversal algorithm, it's going to find all the nodes in I because they're all reachable, right? Suppose I start the DFS here, my run, right? Is it going to find all the components inside? Why? Because they're all reachable. But is it going to reach to any other component? No. So my plan here to detect these components is to start the traversal algorithm in the last component. That makes sense? Because here's my thinking. If I start the DFS in I mean, you could say, okay, how do you know how to start in I? I don't know how to start in I. But if I manage that, my DFS traversal or BFS traversal, whatever I want, is going to find all the nodes in that component. And it's not going to get out of it. Why is not going to get out? Because there's no edge coming out of I anywhere. So you can't, any traversal is going to start exploring. It's going to reach all the nodes because they're all reachable. Anywhere I start, I can reach anywhere else inside that component. But any traversal algorithm will not manage to get out of it. So as long as I can find any node in that component, that last component, and I run a DFS or BFS from it, that is going to identify the whole component. Make sense? So I'm going to say that in here. That's the first point. The second point is a DFS start in I will only traverse exactly I nodes. My point is if I manage somehow to start a traversal algorithm in here, I'm going to identify all the nodes in that component because they're all reachable, but I won't jump to any other component. Is that something you guys believe me or not? Hands up. Okay? No? So this is an analysis. I'm not yet running any algorithm. I'm saying if this is the situation, what I need is to start a DFS or BFS in I somehow. Because if I do, I'll say when that run is done, when the algorithm says I found all the nodes that are reachable from where I started, like BFS and DFS, they all have these runs, right? If you didn't finish, start another one. That would be exactly one strongly connected component. Because it's going to reach all the nodes in I, but it's not going to get out of them. But how do I find a node in I? The graph is not DAG. The SCC is a DAG, but the original graph is not. Right? So can you run anything to identify one of the nodes in I? Right? Again, we said if you can start the traversal in I, that's going to find the strongly connected component. But how do we find any node to start the traversal in I? Okay, so I run DFS first, just to figure out if I run DFS in this graph. Can you tell me what is a node in the last component in DFS? Is it guaranteed to be this the last finishing or last discovery or anything like that? This I mean, if it's I can imagine there's more nodes in here in terms of strongly connected components. It's just one. But say I have two nodes, it really won't change a thing, right? Can I run some sort of algorithm, stage one, just to find any node in I? Because I already know that if I have a node in I, starting a new traversal in that node is just going to identify that component, right? Do we agree with that first statement? The problem is, how do I find a node here? Say I run DFS. All those problems rely on DFS, because BFS cannot do more than DFS. DFS does everything that BFS does and more. So if I run DFS, I don't know, DFS is not guaranteed to start anywhere. DFS will start at random in some node like C. And then what's going to happen? CD is going to reach in I, right? Can I run DFS and at the end of DFS put my hands on a node in I? How? Or why? Or not why? Everybody follows what I'm doing here? My stage one purpose is to find a node in I. This will be stage two. Stage two, right? Right here. If I have a node in I to start my traversal, that's going to be easy. I'm going to identify the component and move on. Perhaps once I get done with that, I will need now a node where? What will be my next component to identify?
That's also in that.
Which is CD, right? So if I'm done with this, I'm saying I can output that strongly component, remove all the nodes and all the edges incoming to it. My next component will be the one that has no outgoing edges. Again, the same principle, except I have to find a node to start in it, right? So can I identify a node in I first?
If the finish time is equal to discovery time.
That's not, that's never happening. Maybe closer. I'm not sure that's
The earliest finish the first.
earliest finish time.
Yeah, the node which gets that.
So in here, this I is the one that finishes, that's what people are saying. The way you identify this component, some node in this component, is run DFS and look for the earliest finishing time. Is that true that the earliest finishing time will be this I?
Where you start.
Where you can be unlucky and start where you don't want. Where can I start so that the earliest finishing time is not I?
No, you take
If I start in A, what's going to happen? I reach, where's the node that finishes first if I start in A? I get to B, get to E, then I get to F, right? I think in this example, it's I is going to finish first. But that's just an example. Let's think, is that a general statement to say, wherever you start in a graph, the earliest finishing time will be one of those components that have no outgoing edge? Is that true? Suppose I don't have this edge here. The components will be the same, correct? Now, if I start in A, I go to B, then I go to E, then what happens next? E finishes. So I think in that example maybe was true, but in general it's not true. That's one of the most difficult problems with graphs. Figure out something that you believe, like this hypothesis we just had. The earliest finishing time is in one of these DAG late components. Is that true in general or not? Because for my example, I draw 3, 4, 5 graphs, it's all true. Well, find an example for which is not true. That's one of the major items in problem solving. How do I know that somebody throws an idea at me And I'm saying, okay, sounds reasonable for 2, 3 examples. How do I know it works all the time? When you grade exams, you have to do a lot of this because people write all kinds of fantasies. And some of them are quite reasonable. And you have to figure out, okay, why is this not working, right? And when you get that experience with grading, I'm appearing a lot smarter because I've seen so many people running ideas that work for some cases but not other cases. You get a lot of experience with this. Okay, so that doesn't work. Then what? Can I identify a node in I?
You could check if like go from X to B and then I, like so I has no outgoing edges, like even separate.
But how do I know? I in here is one node, but in general it's a component of nodes, right? So I think this is misleading a little bit. Maybe I can have also a J here and maybe a K, so it looks like this. Right? So if I just go by no outgoing edges, they all have outgoing edges, but just in between. This is still, let me write it this way. This will be the component what? IJK here now. Now I still want a node in that last component to start my second stage from there. But I can't just say there's no outgoing edges because as far as the graph is concerned, when I'm traversing it or when I analyze it, stage 1, I see a lot of outgoing edges in here. So I think everybody can follow me in that I want 2 stages, a stage 1 and a stage 2. Stage 2 is just once I identify a node in this component, it's easy stage 2. I just start in there, do a traversal. I know it's going to find all the nodes in the component and nothing else because you can't get out of this component. Problem is in stage 1. How do I find one of these nodes, IJK? Hmm?
Baggage.
Backage?
Yeah, like if we traverse from A to suppose we reach I. So now I is grey, now we are traversing from to J and then K. And then we reach again I. So it is a package.
But I can find this package first, maybe, right? I can do A, B,
Yeah,
E,
so
E, and now I find the package, and I mean not, I found the package like you say, but I'm not in component IJK. I really want a node in IJK, because see, my second stage cannot start in here. Can I start the second stage here and say, okay, if I start in here, identify this component with the second stage? Why not? It's gonna identify this component, but it's also, if I start a traversal in one of these nodes here, can I say that traversal is gonna only identify F, G, and H? No, because there are outgoing edges to other components. I need to start in a component from which there are no outgoing edges to other components. How do I identify one of these nodes?
first we can like find all the cycles in the graph. And like then
All the cycles in the graph? That's a lot of them. Could be a lot.
First cycle maybe then.
Okay?
Can you build components and then do the
And then yeah, and then like see all the outgoing edges from that. And then like find the other cycle like which is from that outgoing edge.
I don't know if that works, but the way you said it, it seems like at least a E-squared type of algorithm. Seems like a complicated thing. I'm looking for something quicker that identify a node in this component. That's the one, that's my plan. Stage 2 must start in here. As long as stage 2 starts in here, I'll be okay. But I can't start in here or there because that stage 2 is not just gonna go through one component. It's gonna go more than one component.
Can you find the node that have 2 more in degree than the out degree?
2 more in degree?
Yeah. I mean, more than 2.
But I don't think 2 is a magic number here. If I can find that, it's not guaranteed to be in this component, right? Could be some other component.
On similar lines, maybe if the out degree is more than the in degree, then that can be.
I don't think that will put me in here. If I could have, what you say, the in degree is bigger or out degree?
Out degree is
So in this, the out degree is what? You mean the total out
bigger.
degree?
Sorry, in degree bigger.
In degree bigger.
Yeah.
But you mean in degree as a set? Or in degree for a node?
For a node. As have.
So in degree is 3 to 1? You think I can have a component that has more than 3 to 1 in degree in some one of the other ones? I mean, maybe not in this example, but I think I can draw one of these FGH, right? That has, I put another node here, has a lot of in degrees to it. I mean, every one of these nodes go to here. It's 5 to 1. And that's going to be bigger, right? It's going to ruin your method.
If we see the first black node without any outgoing edges, the first black node which has no outgoing edges.
That may not exist. Every node in here has some outgoing edge. Look at this graph. There's no node without outgoing edges.
For example, we traverse and we reach to I at one point and we go to J and K. So we make K black node and then J black node and then an I will become a black node.
But you don't think that can happen here too? I mean, my guess is that what you're describing can easily happen in other components. Not necessarily have to be the last one. So do we all realize that the stage 2 is easy? Once I have a node here, starting a DFS in there, it's a done deal. But the stage 1 is hard. Finding a node in IJK. I actually don't think it's possible. So I'm giving you a hint. Okay? I can't find a node in IJK. But can you find me a node in ABE? ABE is the other side. We were looking for the DAG. We know the DAG components can be sorted in a line, right? Because it forms a DAG. And we are saying, can you find me a node in IJK by some simple traversal method? And we try what, how many? 6 ideas? Nothing works, right? Okay, can you find me a node in ABE? ABE is one of the components. Doesn't have to be just one, right? I could have another component here that has no incoming edges. There are 3 nodes or 4 nodes, and they only have edges towards the other components, right? So there could be more than one component with no incoming edges. Could be more than one component with no outgoing edges. We are trying really hard to find a node in here, one of these with no outgoing edges. We couldn't do that. I'm asking, can you find me a node in one component that has no incoming edges?
Can you build components like run DFS, get the black node?
What's a black node?
The one which finishes early, and then see which all nodes, all the other nodes which can reach to that node. Like for example, E. E is, if you just run DFS, E is the first black node. And then you say E, B can reach E, so B, so that belongs to that component. Then A can reach E2 through B.
But what if you assume that it goes A, B, E? But what if it's A, B, F, G,
Yeah.
and never goes back to E? I mean, it goes back to E after he finished this component, it goes to B and now goes to E.
No, you just find a path that from every node you have a path to E, so you have to check that. And if there's
So
a
if
path
I run a DFS from A, I may discover the whole graph before I reach to E, right? It's possible. Because I can go to E really quick, or I can go to E. I can control how DFS is going to choose its edges. You see what I'm saying?
No, what I'm saying is you get the first black node, whatever it is, need not be E, it can be anything. And then find all the vertices which can reach to that black node, so those belong to a component.
So I get the black node and I go through all the edges that reach to that black node?
Yeah, and make that happen.
So I think I can get that black node to be one in here, but I'll have an edge from another component to it, which is not going to work, right? If I get start in A, one of the first black nodes will be in here, in FGH, like you say, but then I'll have an edge from this component to that black node. For example, I think I can get F to be the black node, but I still have an edge from E to F. So then I can't say E is in the same component with that. Let's not run wild. Let's stick with the strategy here. I still want to do that. I want to find a node in here that I can run stage 2 on it. Because I know if I start in this, am I guaranteed to just stay in there? I couldn't do that. Just for fun, can you find me a node in ABE?
You just run DFS beginning from entry node.
Yeah.
And if you finish, then that node is the one in ABE. If it's not,
What do you mean if I finish? I'm gonna finish.
I mean you.
I run
all the-
DFS first,
Yeah.
and then how
all
do
the
I?
node is discovered. All the node is.
All the nodes are discovered, all the nodes are finished.
Yeah.
Can you tell me which nodes are in ABE?
What?
Can you give me a node in ABE?
I mean the one that you begin from is the one.
Maybe I start in G.
But if you start in G, you cannot finish. You will only finish like.
Right, I can't get to this component if I start in G.
Yeah, then you run it again until you finish all the node. And then the
So
last one is.
I want to formalize this idea. Can I run DFS? I may have to run multiple runs, right? Because if I start in G, I'm going to finish these components, but not this component, so I have to do another DFS. After all these runs, can I look at discovery and finish times and find a node guaranteed in ABE or in this one? Those two components are the ones that have no incoming edges. I would like to look at discovery and finish times and say, give me a node in here. No incoming edges.
So biggest finish time.
Correct. The biggest finish time after all DFS runs are done, it's guaranteed to be in one of the components with no incoming edges. Let's think about that. If I start in this component, I explore the graph, but where I'm going to finish? I'm going to finish in this component, right? Because once I start from here, explore, 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 come back, come back, come back, I'm going to finish here. If I start in here, I'm going to explore the graph, finish what I have to finish. I'm not going to be able to reach this side. So later, I'm going to do another DFS run that starts in here. And then it's going to finish after all that. So my second big point here is the biggest or the last finish time is a node in SCC without incoming edges. So the last finishing time when I run DFS, doesn't matter how I run it, doesn't matter what I start. I could start here, I could start here, here. The last finishing time must be in a component with no incoming edges. Why is not possible the last finish time to be here? This component has incoming edges, right? Because if my DFS, when I explored this, started in here, it can't possibly have the last finishing time in this component. It has to be in that one. And if it started in this component, it's going to finish in this component, but then later on, I'm going to have to discover the component before it. Because starting here, I can't reach this component. So the last finishing time, no matter how you start, it's got to be one of the components that has these are important components. So these are SCCs, those two, with no incoming edges. In other words, in the topological sort, where would those components be if I just sort the graph? On the left side, right? So I'm going to say this is another component 1, 2, 3, 4. That component is here, 1, 2, 3, 4, right? It's got to be on the left side of the topological sort, the ones with no incoming edges. Just like the one with no outgoing edges have to be on the right side of the topological sort. Who's with me? So I wanted to find IJK, a node here, but I couldn't. We tried, what, 6, 7 things? Don't worry. Maybe you go home and you find one. But I could find very easily a node in here in ABE. That is the other side of the topological sort. Strong components that do not have incoming edges. How is that helpful? I found a node. Can I run stage 2 starting in ABE? If I run that, if I run now stage 2 starting in ABE, it's going to do what? Discover the whole graph. How can I now start an ABE and just stick to ABE? So I want to say, okay, I found a node in here or here. And I would like to start a DFS to only stick in this component. It's the opposite of this, right? This doesn't reach anywhere. And this one is not reachable from anywhere, but it can reach a lot of the graph. How can I start in ABE, a DFS, and just stick into ABE? I run a DFS from B or E, or it doesn't matter which one. But I need to do something to not get out of it. Right? To be able to have that stage 2 property, it discovers everything inside, but it's not able to get out. It's able to get out because of these edges, right? So how can I do this?
Change the direction of the edges.
Very good. If I change the direction of the edges, I claim I can still reach anywhere. Right? Suppose I start in B. If everything was reachable, this was a strong connected component. When I change all the edges, everything is still reachable inside that component because there was a cycle, reversing the cycle, everything is still reachable. But everything that was unidirectional reachable from AB to the rest, now it's not. So I couldn't find a node in IJK like I wanted. That was ideal because from here I can't reach anywhere. I could just discover IJK. But I could find a node in ABE. And I need to run stage 2 now to just stay in ABE. To do that, I'm going to have to reverse the edges, all the edges in the graph. So stage 2, the way we actually going to do this. So I think we have an algorithm now. SCC, fine. We said what? Run DFS, stage 1. Get nodes with highest, what did we say? Finish time. This is stage 1. Right, we already said that. Stage 2, run DFS, but on what graph? Graph with V and reverse edges. Run DFS on this graph. Starting where? How did I pick up that node in ABE?
From the result of the research one.
From the highest. I'm going to call this F1 from stage 1. F1. So what's going to happen if I reverse these edges and I start in ABE? I'm going to discover ABE, but not be able to get out. Right? And then, what? Are you guys follow me? So I run the first DFS. The highest finishing time will be somewhere in here. Okay? Then I reverse all the edges. I start in here. I discover ABE. And then, can I go by the next finishing time? Is that guaranteed to be here? If I say, okay, you do the first component, we know that because we are in ABE. Now we're saying, once that's done and I remove that old component, because I printed out, that's my first component. Can I repeat and say the next largest finishing time has got to be between the remaining components, got to be in this one? I think that's true. The first DFS will not be able to finish a node here before a node here by the same reasoning as before. Even if it starts in ABE or doesn't start in ABE, or starts in FHH or the CD or whatever, I say the discovery time, the finishing time in here has to be later than here. Because if a DFS run includes both these components, then it's going to include this one first. And if a DFS run includes this component first, then it's discovery finish. Later on, it's going to have to deal with this one. So this idea is one of the things that's master level but no undergraduate level. That the first DFS runs has bigger finishing times in ABE than in FHH than in CD. So there is a theorem that says, given my DAG of SCC DAG in here, the finishing time of everybody in ABE and everybody is 1, 2, 3, 4. I have no comparison between those two. But this guaranteed to be bigger than finishing time of FGH. Right, because there's an arrow of 1, 2, 3, 4 points here, then this is also bigger than f of FGH. And this FGH is bigger than CD. And also bigger, this is bigger than CD, and they bigger than f of IJK. So that's something you need to be able to prove that. This is stage 1. The finishing time of the first DFS, if this is the DAG by SCC, everybody on the left side gotta have a finishing time than if somebody in the right side. It's not possible for DFS, no matter where you started, to finish CD after ABE or after FGH. And based on this idea, stage 2 must run starting from these components with high finishing times and reverse edges. So in this way, I'm going to produce SCC components. How much is the running time here? This is V plus E, right? Just DFS. Reversing the edges takes E time, because I just look at all these, reverse them. Another DFS. So this is only V plus E. Okay? That's how we find strongly connected components, and this is a basis for very interesting problems. This idea of strongly connected components. Because I'm a little behind, I want to introduce something that we can't finish, so we'll have to do it on Friday. Usually we don't spend so much time here, but I feel like that was a good exercise. So what I'm going to say now, I'm going to recap on Friday, but I want to introduce that idea, which is we have graphs now that have V and E, but every edge, UV, has a weight. So the weight on UV is a real number. So I don't just have connections like before. I also have some weight. This could be cost, benefit, length, bandwidth. Depending on what problem I model, every edge might have some sort of quantity associated with it. If it's a water pipe, it has to do with how much water can pass through that pipe in a unit of time. If it's an internet connection, it's the bandwidth. If it's a road from Boston to New York, it'll be the length of the road. There's some weight on the edges depending on what problem I'm modeling. And I'm going to define the concept of minimum spanning tree. So as the name says, it's got to be a tree. A tree means have to have exactly d minus 1 edges, connects all nodes. Right? No cycles. That's a spanning tree. I may have other edges in this graph. Right? I may have this edge, I may have this edge, I may have this edge, this edge, this edge, this edge, this edge, so on and so forth. But they're not used. The edges being used are this edge. So is it clear what I'm trying to do here? I have a big graph. I'm trying to find a subset of the edges that forms a tree, called spanning tree, because it connects all the nodes in the graph. In some sense, DFS, if I can do it from the first run, right? That first run traverses the whole tree. Isn't that creating a spanning tree? The DFS tree isn't it connecting everybody? But in here we don't have direction of the edges. So DFS is a very particular algorithm, important in directional graphs. But in here we're not gonna. It's undirected. What do you think minimum stands for? Minimum what way? What edge? Minimum refers to total weight on the three edges. So I'm not going to consider the weights on the other edges. I'm only minimizing the edges that have been selected. Note that the spanning tree is not unique, right? I could have replaced this edge with this edge, right? And this is the unselected edge. Now that's a spanning tree too, right? And there are many spanning trees that connects all nodes. I need to select the minimum one of them. And even the minimum, if these edges will be equally 1 and 1, the same weight, even minimum spanning trees could be more than one, because I could use either one of them and both give me a minimum spanning tree. Minimum spanning tree is not unique. Before we do spanning trees, of course the job here is to find a minimum spanning tree. These are very practical problems because minimum spanning trees are very related to all kinds of minimum cost of, say, UPS delivering packages. How do I drive such that the total drive is not too big? Distribution networks, when I have to move the water from the station to everybody, right? I don't want to move it to more pipes than necessary, but I have to distribute water to everybody, so I need a spanning tree. The water graphs from a spanning tree, right? There's very practical problems in the graph have to do with minimum spanning trees. Even on social graphs, how do I go through all my friends and all their friends? Essentially, I'm building a spanning graph of my connections, and I have to define the edges as click time, or running time, or waiting time, something, or effort to go through my friends' posts or something. And I don't want to spend too much time go through everybody updates posts, right? You can define many spanning trees in very, very practical ways. So having a big graph and determining spanning tree, it's a practical problem. Before Friday, we're going to figure out how to do spanning trees. But for now, I want to show you the principle of a spanning tree, of spanning tree construction. Not the actual algorithms, those we're going to do on Friday. So, MST theorem. It says, I've already have greedy and correct partial minimum spanning trees. What I mean, I've already have decided somehow that this is a good part of the spanning tree here, and this is a good part of the spanning tree here, and this is another good part of a spanning tree. So I already decided somehow this is a node that's not connected to anybody yet, and this is another component. So I decided somehow, I don't know how, that these edges are going to be part of my spanning tree. Again, a tree is a subset of edges. That's what it is. I'm going to pick the edges from the original edges of the graph. So of course I have a lot more edges here, but so far I decided that these three edges are good, these three edges are good, these three edges are good. Obviously, I don't want to add an edge like this, right? Why not? That can be, once these are for sure edges in a greedy sense, I can't go change them. This edge, independent of its weight, cannot possibly be good because it breaks the tree, form a cycle. So what are the edges that are possible to add in here? Any new edge that I decide to add, for when anyway, it doesn't have to be greedy, but assuming I'm not willing to change the existing edges, because I pick them greedily, they stay. What are the options for my new edges to add? Connect two of those things. That's the only way, right? So a new edge must connect two existing trees. Because otherwise, any edge will form a cycle if it's in the same tree, right? So here's the theorem. The theorem says, define a cut in the graph. Partition of nodes, all nodes, into two sets, left and right, respecting existing edges. So I already have some edges. What's a cut? I have to partition the nodes into two groups, left side and right side of the cut. But I have to respect these edges. What respect means here? If I tell you, partition those nodes any way you like, left versus right, it's a two groups partition, but you have to respect the edges. It means the cut cannot cut the edge. So my cut could be here, for example, because this cut doesn't have any existing edge going left to right. But that's not the only cut I could do, right? I could draw another cut that is like this. Delete this one. This is a cut. It respects the edges, right? It doesn't take any existing edge going from left to right. So respect means no edge left to right in the sides of the cut. Do we see this? This is a very simple principle. I have to find a cut that, out of many possibilities here, take some nodes on the left, some nodes on the right, but no existing edges go from one side to the other. So this cut is not unique. Then the theorem says, next edge is greedy, is the smallest edge left to right. What this theorem says, once you find your cut, for example this cut, if you took the minimum edge growing from one side to the cut to the other side of the cut, right? For example, this edge here, if I have one, this one here to here. This is minimum edge across the cut. This edge, you can add it to your spanning tree. It's called safe edge to add. Now why is that? Why adding this edge is good? Guaranteed. I don't have to go later on and change it.
Because both are subproblems and minimums.
Because eventually those two sides have to be connected. If it's not the minimum edge connecting them, it will be some other edge, which is not minimum. This one will be better than that one that eventually connects the edges, right? Because I have to end up in the very end with a connected tree. So if the edges will be something here, and that's not the minimum, this is a 2, that's a 7, I could take that one out, put this one in, like in greedy algorithm, exchange arguments, and this one's the better edge. So we're gonna have to talk about this theorem next time. This is the basis of all minimum spanning tree algorithms. The only difference between algorithms is what is not unique in here. This is the principle of all minimum spanning trees algorithms, which is not just one. We're going to study two. But what can they do different? Why can, if all trees have some build-up tree and then define a cut and then find the minimum edge across the cut, what can be different between two minimum spanning tree algorithms? No, we always try to optimize the minimum edges. The cut. There are many possible cuts, so different algorithms will define the cut in different ways. But once they define the cut, what will be the next edge? Minimum across the cut. Guaranteed. So they're all going to be greedy algorithm, just different definitions of this cut.
Is the collection of partial complete? Do they?
Some of those are not connected yet. So in some algorithm, maybe, let me do one more thing here. In some algorithm, maybe I only keep a tree, right? I have an existing tree. That's a tree. And everybody else is disconnected. If I want to keep this tree building up, I don't want to have this situation. How should I define the cut? So the next edge that I'm going to add, which have to be the minimum across the cut, it's going to certainly connect to my partial tree. How can I define the cut to have that effect? I just take the existing tree, isolate to everybody else. Is that a valid cut? Yeah, it doesn't intersect any edges. Now I say find the minimum. Again, cut can be designed any way you want with a condition to respect existing edges. Now if I find the minimum edge across this cut, in this situation, it's going to be from some of these nodes that are already connected to some other node that's not connected, right? Because all the edges across the cut looks this way. So essentially this algorithm that defines the cut that way will always grow one tree. This algorithm maybe defines the cuts differently, so it can connect some nodes that are not already in a tree, so it's a bunch of small trees. And every cut, it's going to connect two trees, right? If my cut is in here, it has those two trees versus the other, there's some unconnected nodes, right? It's going to connect one tree from left side with one tree from the right side. Some of these trees might be one node trees. Maybe it connects this tree with that single node. That's the cut. So the cut's definition can be very different, but once you define the cut, these algorithms will always pick the minimum edge across the cut. Okay, there is a homework related to all this, right? How are we doing with those demos? How many people demo all three coding problems? All three? No one. That's not good. How many people demo two of the coding problems? Okay, so are you guys, which problem you didn't demo?
The third one,
Fibonacci heaps. But is it done? Just waiting for the demo? Good.
I think the binomial.
Binomial heap is fine. Fibonacci heap is for people who want to spend more time on them.